Hello and welcome. We continue today with our chemical energy storage section and continuing with the discharging technologies from our chemical storages. And there is a very good information. We don't need to learn anything new because that is one of the advantages going for power to chemicals, for power to liquid, for power to gas, that the discharging technologies remain those that we already nowadays apply in our daily life. So we can talk here, or we can use the renewably generated natural gas, for example, in combined heat and power technology that uses today natural gas. The fuel cell technologies, gas turbines, combined cycle gas turbine power plants, low temperature gas boilers, condensing boilers, gas-driven heat pumps, gas-driven absorption heat pumps, Otto engine, jet engines, and for sure many more. And just to get an overview, this for example is an example of a combined heat and power system driven by a gas engine. And the mechanical power is used then to generate electricity in an electrical generator. And the waste heat of this motor, so the flue gas heat is used in a flue gas heat exchanger. The motor heat is used in a heat exchanger for the motor. And that heat can then be used for heating purposes of houses and buildings, for example. So it's the application of our renewably generated gas in the heating and in the power sector. Or we can completely use it in the heating sector, for example in this low temperature gas boiler, or a bit more in advanced technology in a condensing boiler. Natural gas, as well as the renewably generated, also contains some water in a steam form when it is burned. And there is a lot of energy contained, and when you then condense this water, we can increase the efficiency of those boilers. Sometimes we see that the efficiency is more than 100%. That for sure is nonsense. It's only marketing, or it's a wrong physical constant where we put that in relation, but for sure efficiency is not higher than 100%. Then we can use the stored gas in the mobility sector, just using it, for example, in the Otto engine. Or we all know, again, coming to the heating sector, nowadays we operate a lot of electrically driven heat pumps. But of course we can just substitute the electrical motor by a gas-driven motor to operate the compressor of a heat pump. So starting using the ambient heat down there in the heat exchanger, in the evaporator, then the gas motor is compressing the evaporated cold medium, and then in the condenser we gain that heat on high temperature, using it for heating system before we decompress it in the throttle, and then the loop is closed. Or we use it in fuel cells. It's a direct conversion of chemical energy into electrical energy without a generation of thermal heat by combustion in between, like in power stations. And that is named also because of that, the cold combustion. It has high efficiencies, also in part loud conditions, has low noise and other emissions, but of course is still expensive when we compare that to other discharge technologies. In the video we see the working principle of the fuel cell technology. To sum up, we have different fuel cell technologies that we see also here in this illustration. We have the alkaline fuel cell, a direct methanol fuel cell, the DMFC. We have the molten carbonate fuel cell, the DMCFC, the phosphor acid FC, the PAFC, the polymer electrolyte membrane FC, the PEMFC, and the solid oxide fuel cell, the SOFC. They all vary in their components they use, but from an application point of view, they have different abilities in their flexibility, in their dynamic operation, that they can go in change of power, and also they vary a lot in the temperature level they are operated. Then we can have gas turbines and combined cycle gas turbine power plants. And today they are used for peak power supply. They are normally powers starting with a few kilowatts up to several hundreds of megawatts. And their characteristic is a very short start-up time of only a few minutes up to a quarter of an hour. The ideal thermodynamic cycle to compare this process would be the Joule process. And whereas gas turbines have an efficiency of a bit less than 40%, the combined cycle power stations can achieve efficiency of even more than 62%. How are they doing that? Here we have a sketch, and on the lower part we see a conventional, not a conventional, but it's a gas turbine, and there we see coming from the left side we see the generator, but first then we see the compressor that is all on one axis, and then we have the gas that is burned, and then we have the expansion turbine that drives the generator and also the compressor. And of course then this turbine is exhausting a hot flue gas, and normally, for example, in an airplane the hot gas is just emitted. And here in the combined cycle this hot gas is used to evaporate water of a steam power plant. And the evaporated water is then decompressed in a steam turbine, and again electrical power is produced. What we see here more on the upper side. And then of course, like in a steam power plant, the low pressure steam is condensed in a condenser, and the water is circulated by means of a pump. And by this double use of the heat of the gas, we get these high efficiencies. Nowadays we use that with natural gas, with fossil natural gas, but in future that can be renewably generated gas, but the power station remains the same. That was a short overview of some technologies, and then we end up with this video section looking a bit on complete power to gas systems. Thank you very much.